Hey everyone, welcome to another session of CeerazzleDazzle Physics. In today's lesson, guys, we're going to be talking about the movement of charged particles in electric fields and combining it with SUVAT, guys, which is the mechanics side of physics. Hopefully you have a good understanding of what electric fields are. If you don't understand what electric fields are, please make sure you watch the videos in my description before watching this video, otherwise this video just won't make sense. Okay, right, let's get straight into it. Alright, so over here I'm going to have a simple electric field. So look, we've got two plates. The top plate will be positively charged, okay? And then the bottom plate will be negatively charged over here, okay? Easy stuff. Right, so hopefully you identify that the electric field lines go from the positive to the negative. Why? The field lines show you the direction which a positive charge will move in. So if I was to put a positive charge in this field, it would move in this direction towards a negative plate, obviously because it's positively charged. So look, the field lines are going down like this. Obviously make sure you use a ruler in the exam and you make sure that they are equally spaced. Okay, so now we've got an electric field and we've drawn our field lines. Now let's fire a particle into it. So let's just fire an electron. So here's an electron right now. Hopefully if we fire the electron in, yes, let's say it has a velocity u initially. So we know that it will enter, and because it's negatively charged, it will curve upwards over here. Very good. So we know that charged particles will be deflected within an electric field. Because it's negatively charged, it will move upwards over here. And let's say, for example, if I was to put a positively charged particle, so let's go for an alpha particle over here. So alpha, which has a charge of +2, obviously it's going to travel this one over here and be deflected away from the positive terminal and going all the way over here. There we go. Easy stuff here. So we have an idea that charged particles will be deflected with an electric field. But right now, guys, we're going to try and combine this with some mechanics. Okay, so from here, you might be thinking, I've never seen anything like this, but we can tie this into mechanics. This is very similar to gravity. So look, on this side of here, this could be the Earth, and look, we could have the gravitational field lines going downwards over here. And obviously, if I was to fire, let's say, an object with mass into it, first of all, we know that, yes, it will also experience the field, and therefore its trajectory will change over here. So in this example over here, hopefully you remember that we can use SUVAT over here, so we can use mechanics to solve this problem. And therefore, guys, hopefully you can see that I can use SUVAT in this example as well. So SUVAT can be found in gravitational fields, but now we can also see that it can be found in electric fields. Right, so from here, everyone, I'm going to give you an exam question so that you can see it in action. You can see how electric fields and SUVAT both are combined together. Okay, right, so check out this question. Question 17. An electron is projected into an evacuated space between two charged plates of length 5 centimeters as shown in blah blah blah. The electric field strength is 3.5 times by 10 to the 4 newtons per coulomb. The velocity of the electron v is 3.2 times by 10 to the 7 meters per second. Neglect any gravitational effects. Right, there we go. So here's our electron is fired in here, and as we can see, we've got the positive plate at the top, negative plate at the bottom, and that's the strength of the electric field. And look, the length of this, this bit of this plate over here is 5 centimeters. Number 1. Well, A. What is the size and direction of the electric force on the electron? Right, so hopefully you can remember that the electric field strength is equal to the force acting per unit charge. So therefore, if I want to work out the force is equal to the electric field strength times by the charge. The electric field strength, we know it's going to be 3.5 times by 10 to the power of 4 multiplied by the charge. What is the charge? Is the charge of the electron itself, 1.6 times by 10 to the minus 19 coulombs. Okay, so let's do it in a calculator. What do we get? I'm going to get the answer, guys, to go and be 5.6 times by 10 to the minus 15 newtons. So that's the force it gets. So as it enters this field, we know it gets a force. So this electron, as it's in the field, it gets a force upwards. So that means that the force acting on this electron will be upwards over here. The force acting on the electron will be upwards. So that force, which we just calculated, will be pulling it upwards due to electric field. Alright, so part B, it's going to be what is the horizontal velocity of the electron as it leaves the plate? So what is the horizontal velocity? Right, now, hopefully you can see that the field is vertically, yes? So therefore, the horizontal motion is not affected at all by the field. So therefore, the horizontal velocity remains the same. Don't forget, the reason why is because gravity only acts in the vertical plane and it has no effect on the horizontal motion. So we can say that the velocity as it leaves is going to be the same as it initially enters horizontally. So 3.2 times by 10 to the power 7 meters per second. Part C. How long does it take to pass between the plates? How long does it take for me to pass between the plates over here? Right. Okay, so look, you're going to be moving at this horizontal velocity and you're traveling this distance. So that's the time taken. So velocity is equal to displacement over time. Yes, in the horizontal plane. Just looking at the horizontal plane right now. So therefore, the time taken is equal to the displacement divided by the velocity in the horizontal. So displacement in the horizontal is going to be 5 times by 10 to minus 2. Everyone happy with that? Centimeters over there. Divided by the velocity in the horizontal plane, 3.2 times by 10 to power 7. Going to get the answer of 1.56 times by 10 to the minus 9 over here. Excellent stuff. Then it's going to be part D. What is the vertical acceleration of the electron? Right, okay, so what is the vertical acceleration of that electron here? What we're going to do? So we know it's going to get a force. We already calculated that force upwards. This one was 5.6 times by 10 to the minus 15 newtons upwards over here. What would be the acceleration? Well, this is the resultant force. Yes, this is the resultant force. You also know it has a mass, therefore we can work out the acceleration because we know the resultant force is equal to the mass times by the acceleration. Therefore, the acceleration is equal to the force acting per unit mass over here. So the force which is acting on the electron is 5.6 times by 10 to the minus 15 over here, divided by the mass of the electron. Oh, the mass of the electron is not on there. The mass of the electron is 9.1 times by 10 to the minus 31 kilograms over here. So look, over here we have the following, putting that in over here, 9.1 times by 10 to the minus 31. Okay, so in the calculator it goes 5.6 times 10 to the minus 15 divided by 9.1 times 10 to the minus 31. I'm getting the answer of the acceleration 6.15 times by 10 to the power of 15 meters per second squared over here. Question E. What is the vertical velocity on leaving the plates? So if I want to know the vertical velocity when leaving the plates, obviously I'm looking at the vertical plane. So let's try and look at SUVAT in the vertical plane. Let's do S, U, V, A, and T. Right, what do we know already? The acceleration was 6.15 times by 10 to the power 15. Yes, that's going to be my vertical acceleration over here. The time taken, don't forget the time taken for the particle to move all the way across over here is the same as the time taken for it to move vertically upwards to the top plate. Both the times are the same. Yes, a little bit of projectile motion mechanics embedded in there. So the time taken, we know it's going to be 1.56 times by 10 to the minus 9 over here. And then finally, the initial velocity in the vertical plane was what? Well, initially it was only moving horizontally, so the initial velocity in the vertical plane is 0. And now all you're trying to do is find v. So we can use the following formula. V is equal to u plus at. So v is equal to the initial velocity 0 plus 6.15 times by 10 to the power of 15. Good, times by the time taken, 1.56 times by 10 to the minus 9 over here. I'm getting the value, guys, of the final velocity in the vertical plane going to be 9600000. Yes, meters per second, the final velocity over here. I'll just put a line under it so you don't get confused. This was for this question, these are for this ones over here. Then finally, part F. What is the size and direction of the final velocity? What is the size and direction of the final velocity? So we know that as the particle exits, it's going to have horizontal velocity moving it across, yes, which was going to be the same as this one over there. It has but also it will have a vertical component now because it accelerates. So therefore, if I want to work out the final, obviously it's just going to be a bit of Pythagoras over there. Yes, just to find this out here. So I'll just draw that one out over there. So we know that it's going to be this bit over there. We're trying to find this out. We know horizontally it didn't change the final velocity. So this one was going to be 3.2 times by 10 to the power 7. The vertical velocity was how much? The vertical velocity we just worked out in the vertical plane was going to be 9600000 meters per second. Yes, this one is meters per second over here. So then finally, v is equal to the square root of it all. So it's going to be 9600123 squared plus 3.2 times by 10 to the power of 7. There we go, squared as well. And all of that is going to be square rooted. So therefore, that squared plus 3.2 times by 10 to the power of 7 squared, root the answer. I'm getting the value of roughly 3.3 times by 10 to the power of 7 meters per second. So this value over here is going to be 3.3 times by 10 to the power of 7 meters per second going here. But then don't forget the question itself, that was the final size. I want the direction, so I need this angle as well from the horizontal. So therefore, let's do this one. This one's going to be, we can do tan, we can do theta, yes. So tan of the angle theta is equal to opposite 9600123 divided by adjacent 3.2 times by 10 to the power 7. Therefore, theta is equal to tan inverse, everyone. Look over here, 960,000. How many zeros? 1, 2, 3. There we go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Divided by 3.2 times by 10 to the power 7 over here. So let's do that in a calculator. I'm getting the angle of theta to the horizontal is going to be 16.6. Well, 17 then. Let's go for 17. So 17 degrees. So that's going to be 17 degrees this angle over here. So my value is going to be this, and let's just do that. Sorry, my value is going to be this, and the angle is going to be 17 degrees. 17 degrees from the horizontal. And look, that's a good example of how we can actually combine electric fields and SUVAT together. And if you're still struggling in any of my content, why not check out my YouTube channel, in which I've got hundreds and hundreds of videos to help you with your studies. And that's it for another session of CeerazzleDazzle Physics. Make sure you hit the like and subscribe button to keep my channel going, and good luck in your studies. Ciao, ciao, and goodbye.